Hey guys, so unfortunately, the Zoom meeting I copied yesterday does not seem to be working. Only the audio is available, so I don't think that's terribly helpful. So I'm going to redo part of the lesson we did on the Zoom meeting, and that's the part that is really the new material dealing with pH of weak acids and strong acids. So I'm going to switch over here to our OneNote. And some of this will look familiar. Maybe some of it will be new for you. So I'm just going to turn off my video here, and let's take a look. So we were going over a few questions. One was determining the pH of a 0.01 molar HCl solution, and there we go. Yes, there we go. So what we're going to look at is how do we determine something like that? So you've got this beaker, maybe, and it's got a solution, and you know the concentration of the chemical inside, and you're told that this is some kind of acid in here, and that the acid is HCl, and the concentration of HCl is 0.010 molar. Molarity. Okay, so how do we tackle a problem like this? Well, these questions are actually fairly straightforward, as long as you can identify something about the particular acid you're studying. So if you could turn to your data table on page 6, I believe, yes, page 6, and you look at the Bronsted-Lowry acid-base strengths, and you'll notice that HCl is at the top of the table. It's in that group of 6 that are strong acids. And so you have to remember, strong acids will ionize 100%. So this acid will go 100% in the forward direction. So it's completely ionized, which is actually kind of confusing. I think the first time you might think about this is that really if you have a 0.010 molar solution of HCl, you actually have no HCl because the HCl ionizes 100% in water. So everything has been converted over to hydronium and chloride ions. So this actually is quite useful because we know the pH of a solution is determined by the concentration of the hydrogen ion, or in our case, hydronium. And I'm being bombarded with people trying to get a hold of me. Mr. Johnson's just contacted me. All right, sounds good. Okay, so if that's true, then the concentration of the hydrogen ion should be the same as the concentration of the original acid. If that sounds a bit confusing, think of this for an example here. Let's say you had a bottle, and on the label you read 1 molar NaCl. Well, you should know that NaCl is a soluble salt. So when you put that into water, you get sodium ions and chloride ions. And really, you would have no actual NaCl in that bottle. Everything would have been dissociated into ions. And so really, you would have no NaCl. It's not actually technically 1 molar NaCl, but it's 1 molar sodium ions and 1 molar chloride ions. And so you can use the same analogy here for a strong acid like HCl. There really is no HCl in solution. It's all converted into ions. So we actually know the concentration of the hydronium would be 0.010 molar. It's just 10 there, actually. And so if I use my calculator here, now if you're a Math 12 student, you might not need a calculator for this kind of question, but the negative log of 0.01 is 2, and my number has 2 sig figs, so I have to go 2.00. The first number to the left of the decimal, or any numbers to the left of the decimal, are not significant, only the ones at the end. So that's actually fairly straightforward. You just negative log the concentration of the acid, and that would be true for like sulfuric acid or maybe hydrobromic acid or perchloric acid. All those strong acids, very, very easy calculations to work out. So that's our first question we did on the Zoom meeting. I'll put a little number 1 there. And then the second question we looked at was the concentration of carbonic acid being the same concentration to determine the pH. So would it be the same as the question above or not? So that was a little bit trickier. If we actually look at the data table for this, we'll notice that carbonic acid is not in the group of strong acids. So it's actually a weak acid, which means it does not ionize 100%. So we should be putting equilibrium arrows between these two sides of the equation. But the carbonic acid would turn into bicarbonate ion, and the water would turn into hydronium. Okay, so the problem here is we can't just negative log that number like we did above, because it's not strong. It doesn't completely ionize over to form hydronium. So there is some hydronium, we just don't know how much. And so if you weren't watching the video, a good question to ask yourself was, do you think this solution, without calculating it, do you think this solution would have a pH higher than 2 or lower than 2? And do you think it'd be much different, or would it be pretty close? What would you guys' guess be on that? Well, one thing you could think of is that since it does not ionize 100%, the concentration of the hydronium ions would be less than it is above. It would have to be a number smaller than 0.01, because 100% would give us that number. And if you go back to the homework you did before, you can relate the concentration of hydronium to the pH. And so if your hydronium concentration is dropping, so you have less hydronium, what's happening to the pH, do you think? Well, if you lower the amount of hydronium, you're going to increase the amount of hydroxides, and that's going to cause the pH to be higher. You're going to have a higher pH, less acidic overall. So I'm thinking the number's got to be above 2. But do you think it's like, it's going to be like, is it going to be 2.01 or 2.2, maybe even 3? Like that's a big number. Or would you think it would be 15? pH of 15? Well, I think if you think pH of 15, you're probably not awake yet, because it's carbonic acid, so it has to be an acid, so it would have to have a pH below 7. But it's probably above 2, but below 7. I think it's a good guess. Okay, so how would we tackle a problem like this? Well, I'm going to erase this part right here. And what I'm going to do is reuse the equation. Now, because it creates an equilibrium, I'm going to create an ice table here. You can use the R if you want for rice table, but ice is good too. And I'm going to say what I know right now is the initial concentration of the acid is 0.010, and that's before any of the acid has ionized. So basically, it's sort of assumed to have not reacted with the water yet. And we know as soon as it comes in contact with the water, it's going to form these other chemicals. But initially, there would be 0 of those chemicals, 0 amounts of those chemicals. That would have come from the carbonic acid. In the class, I did discuss this. I'm just going to add this right now. Is this? We know that water self-ionizes to form hydronium and hydroxide. So technically, there would be some hydronium in the water, just because water would make some hydronium. But this 0 that I'm writing here, this 0 over here, that is the amount of hydronium that's come from the H2CO3. So before it ionizes, you haven't produced any H3O+. So now as the reaction shifts to the right to make more hydrogen ion, less acid, you're going to get an increase on this side and a decrease on this side. And I'm going to say, let the value of x, let that be the amount of hydronium. Because I know once I find out hydronium, all I have to do is negative log that number, and I'm going to be able to get the pH here. So let's just say that is x. So if you go from 0 to x, you must have added x, and you must add the same amount of x here. So this would be x. And you would deduct x from here, and you get 0.010 minus x. Now you might notice I left out the water amount. So this amount here, I kind of just left that out. And the reason for that is that water is a liquid here. So it's not part of the equilibrium. The equilibrium would be dealing with the aqueous, but not the liquids, and the aqueous ions. Okay, so I need to do a little bit of math here. Actually, a fair bit of math here. But first, I need to have a formula to work with. So you are going to have to show us these things when you hand in your work here. And so the Ka would be the products over the reactants, at least their concentrations. So HCO3 minus multiplied by hydronium divided by the concentration of the acid H2CO3. And from my data table, I can see that that number is 4.3 times 10 to the minus 7. So it's quite small, -7, that's a pretty small number. So I'm thinking the ionization here is quite low overall to give me a number like that. So there must be lots of product, sorry, lots of reactant, not much product. Okay, now the Ka, this little a right here, a there, we want to remember that actually is just a specialized KEQ. So EQ being equilibrium, meaning we have to use the E row to find out the amount of these chemicals. So I'm going to plug these into the formula. X squared, x times x, all over 0.010 minus x, all equaling 4.3 multiplied by 10 to the minus 7. Now, in class, we spent a fair bit of time talking about this at the Zoom meeting, but I want to just reiterate this here, and for those who weren't, just to think about this. If I was to cross multiply right now, and like get my x squared by itself, I'm going to create a quadratic equation that's going to have an x squared term, it's going to have an x term, what we call a linear term, and it's going to have a constant value. And really the only way for you to solve that question would be to use the quadratic formula, or maybe complete the square or some other math technique like that. So I'm going to make an assumption here. I'm going to assume something, my assumption. And the assumption I'm going to make is that this x value is very low. I'm going to make the assumption it's a very small amount that actually ionizes, and I'm going to have to go back and test my assumption to verify that. So I'm going to make the assumption that the value 0.010 minus x is pretty much going to be equal to 0.010. Now, it obviously can't be equal to that number. It would have to be smaller, but I'm going to make the assumption that this change is so small, so insignificant, that my final concentration is going to be almost the same as the original for the acid. And when I do that, when I make that step in my thinking, I get x squared all over 0.010, because I'm saying it's pretty much the original number. And that's going to equal 4.3 times 10 to the minus 7. So let's find out our x value now, see what we think about that. And we'll come back to the assumption at the end of this question and sort of see if it's a good assumption or a bad assumption. So I'm going to say x would equal 4.3 times 10 to the minus 7 multiplied by this 0.010, and then I would have to square root both sides and just keeping the positive root for this question here. So I definitely need a calculator here. So 4.3 times 10 to the minus 7 multiplied by 0.01, and then I square root that number, and I'm getting an x value of 6.5574. And this number just goes on forever. And I'm not going to round it yet. I want to wait to the very end to round it. And so that's my x value. So what was x in the question? Like what did we determine x to be? Well, x could be looked at as being a few different things, but to find the pH, we really wanted to know the amount of hydronium. So this x is the amount of hydronium in solution at equilibrium. So at equilibrium, the concentration of the hydronium ions would equal the number above, I guess, molarity. Okay, now we're trying to find pH. We know that pH is equal to the negative log of hydronium. So that would be equal to the negative log of the number we just got. So if you have that number in your calculator, I wouldn't erase it. I would just now go negative log of that number. And I get a value of 4.183265772. And if I round that to 2 sig figs, because my Ka value is 2 sig figs, then I would say it's 4.18. So remember, that's actually a 2 sig fig number when it comes to pH. Okay, so so that's my number. Now, let's just compare the two questions we did, and we'll go back to the assumption rule and see why we did that assumption. Okay, so if I look at 4.18, that's the pH of, I'm just going to check that again, 4.18. So that's the pH of question 2. So this is this question here. So that's going to be 4.18. Now, if you compare the two numbers, you compare the 2.00 and the 4.88, and you say to yourself, okay, well, it is higher. It's definitely not as high. It's not as low as 2. It's definitely not as acidic as HCl is. you could be sort of thinking to yourself, well, it's only a difference of 2. Like, I mean, it went from 2 to about 4, so that's not that big of a deal. But you have to remember that the logs, the pH measurements, sorry, are a base 10 number, really. So when you go from 10 to the 2 to 10 to the 4, that's a factor of 100. So that actually means the HCl is 100 times more acidic than the carbonic acid would be, even though the two acids actually have the same initial concentration. So they have the same concentrations, but they actually produce two quite different pH measurements. pH 2 is getting quite dangerous to be around. pH 4 is not really as much of a worry, I would say, as a pH of 2. I mean, still acidic. I mean, it could cause a chemical burn and stuff like that, but I think you'd have to have a fair bit of exposure to that. Whereas pH 2, that's getting more acidic than your stomach would be on a good day. Okay, so let's go back to this assumption. Like, why did we throw the assumption in here? Well, the reason we did it is that I didn't really want to use the quadratic formula to solve this question, so I kind of cheaped out here on this. Now, if we try to find out, is this a good statement? One way to do it would be to see if it's actually true or not. Like, so take your 0.010 and minus x. So let's minus the x value of 6.5574 times 10 to the minus 5. So if I take my number, 0.01 minus, say 0.01 minus 6.5, say, times 10 to the minus 5. Well, I'm getting, actually, I should probably, sorry, let me just do it one time. 0.01 minus 6.5574 times 10 to the minus 5. That's better. So I'm getting 0.0099344 and change. And if you think about that number, although it is smaller than the original number, it's not very different. Like, it's quite similar. I mean, it's by a very small margin. So I would say that assumption is a pretty good assumption there. I'm not going to test you on percent ionization, but if you wanted to find out what percent it actually ionized, then you could take the X value you got and divide it by the original concentration of the acid and times that by 100%. So I'm going to say take 6.55 times 10 to the minus 5, divide it by the original concentration of the acid, and then times that by 100%. So if I did that, that's going to be roughly 6.55 times 10 to the minus 8, divided by 0.01, and then times by, but not add, 6.55 times 10 to the minus 5, divide that by 0.01, and then times that by 100. And so I'm getting 0.655%. So percent, think about that. Like, that's less than 1% ionized. So you have a huge amount of acid and very little protons or hydronium being produced here, compared to, say, HCl, which is a strong acid and ionizes 100%. So you're getting quite a difference in ionization on this. So the assumption is quite good. So as far as your work goes, like, what would I would kind of expect you to show me? I would expect you to show me kind of generally the ICE table, what's going on here, your Ka expression, the value, plugging in numbers, and then I would actually ask you to show me the assumption rule, unless you're if you're going to solve it using the quadratic formula, that's okay, but you do have to show me that calculation. You can't just use the Texas Instruments built-in quadratic solver and just sort of say, oh yeah, this is the answer. So I would encourage you to use the assumption rule. It's going to be less writing for you. And then basically just the calculations, and don't forget rounding with sig figs at the very end here. So this will be a question on your next test. It would be a different acid. It could be a base maybe. and different concentration. But generally, it's the same kind of question. And so it's a big question, probably like 4 marks, a lot of work to get through, also a lot of work for me to mark correctly. So I'm going to do one more question. I'm going to scroll down here. And that deals with boric acid. And so this is another question we did in class. And maybe just pause the video and see if you can do this on your own here. And even if you did this question already, try it again. See how fast it takes or how long it takes you, because you want to be sort of quick at these questions, even though they're quite big. Okay, so if we're back now, my initial concentration of my boric acid is 0.0010. My H2BO3 minus is 0. My hydronium is 0. And it's going to have to shift to the right. I'm going to have to make some of these chemicals. I'll lose a little bit here, gain a little bit here. And I'm going to make X, once again, the concentration of the hydronium. So that's X. And I get 0.0010 minus the X value. Okay, so then I say my Ka expression. So the expression is just what I'm timesing out here. So H2BO3 minus multiplied by hydronium divide by the concentration of the acid H3BO3. And that's supposed to equal boric acid, where are you? 7.3 multiplied by 10 to the minus 10, I believe. Let's double check. Yeah, 7.3 times 10 to the minus 10. And I knew that the top would be X, and I know the bottom would be 0.0010 minus X, all equaling a value of 7.3 times 10 to the minus 10. Okay, so what do I do? What do I do? Well, I'm going to make my assumption here because I don't want to deal with this quadratic here. That's not what I want to do. So I'm going to assume that 0.0010 minus X is close to 0.001. And what I mean close to, I mean, like if you actually solve this using the quadratic formula, you would get a slightly different answer. But what you would find is, as long as the assumption is true, that the answer you get, once you round it, would be the same answer as someone who didn't round it. So that's how good this assumption can be here. So it's going to save you a fair bit of time here. So that means I'm going to have X squared all over 0.0010, all equaling a Ka value of 7.3 times 10 to the minus 10. So I'm going to cross multiply here and square root both sides of the equation. So the root of 7.3 times 10 to the minus 10, all multiplied by 0.0010. And that gives me an X value of 7.3 times 10 to the minus 10 times 0.001. I'm getting 7.3. Oh, I gotta square that. Hang on. 7.3 times 10 to the minus 10 times 0.001, giving me 7.3 times 10 to the negative 13, but then I square root that number, and I get 8.5440 blah, 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 times 10 to the minus 7. Now, the X value is the concentration of the hydronium, so it's the same number. That's 8 again, molarity. And then the pH should equal the negative log of that number. So that would be the number I want to put in here. So I'm going to negative log that number, and I get a value of 6.07. So 6.07. So once again, that's even higher than the 4 we got from the last question and the 2. Although in this case here, there's two things that are the result here. One is you have a lower initial concentration. So I think the one above was 0.01. And you also have a Ka value that's lower. So there's two effects here. So low Ka values and smaller amounts of the chemical would produce less changes to the pH itself. So I think that was where we ended with the lesson yesterday. So hopefully this addresses those kind of questions. So this is where we are solving for the pH of a strong acid and also the pH of a weak acid. So hope that helps. And I will stop my recording. And where are we here? Oh, bright light. Okay, there we go. So anyway, so I'm going to stop the recording here. Hope you guys are doing well, and we will there's actually several questions online. And tomorrow there'll be another video and a quiz tomorrow. This Thursday will be a quiz tomorrow, and we'll see how it goes here. Let me just stop here.